Good day to everyone. Today we will see why a single-phase induction motor needs a capacitor at the start. Further, some single-phase motors need a running capacitor too, which will operate throughout its running time. To start with, you will see a single-phase supply with 230 volts and a winding of an induction motor connected to it. Wave pattern of the supply voltage and the single-phase current shown on the graph here. Now what we need is to get the rotor of the motor to rotate like this when power supply is connected. Normally an induction motor has some induction load also acting on it, in addition to the resistive load on its windings. This inductive load makes its current curve to shift, with an angle related to the voltage curve. But here we have taken the condition where the motor is with pure resistive load only. It is for easy understanding, and this condition is when power factor is at 1. So you will see both voltage and current curves start at the same time with 0 value and ends too at 0 value also at the same time. Actually, with a single-phase connection, magnetic field doesn't rotate. Instead, north and south poles are changing rapidly with a speed of 50 times per second if the frequency of the supply is 50 Hz. Pulling power or the torque to start the rotation of the rotor is not provided here with single-phase connection. Here we have shown only one pair of poles with windings, and one would think here that increasing of pole pairs may provide the much-needed rotation of the magnetic field. But it will not happen, because all the additional pole pairs provided here are with the same phase angle, and what we need to do is to provide a winding with a different phase angle related to the present single-phase voltage supply. On a three-phase supply, this issue doesn't arise, since all three phases are with 120 degrees apart, providing the necessary rotating magnetic field for the rotor of the motor to rotate. But for single-phase supply, we need to provide an additional current with a different phase angle only for a short period of time, around 3 to 5 seconds, till the rotor of the motor gets around 75% of its full rotating speed. You know, the conductors on the rotor need to cut the rotating magnetic field to provide the necessary torque required to rotate the rotor of the motor. If you consider a capacitor, its current normally leads 90 degrees, related to the current of a pure resistive load. So if you use a capacitor at the start of this motor, it will definitely provide the necessary phase angle difference required to provide the rotation of the magnetic field. For this, we need to introduce an additional winding to the motor like this, and will be fitted with a capacitor, called start capacitor. This additional winding is normally called auxiliary winding, or start winding. You will see now, this starting capacitor is fitted series to the start winding, but is parallel to the main winding. Further, we need to introduce a special switch to isolate this capacitor from the auxiliary winding when need arises. This can be done by providing a centrifugal switch, and after reaching the predefined speed, start capacitor will be disconnected from the auxiliary winding. Although current will not directly flow through a capacitor, when connected to an alternating voltage, there will be electrons, or so-called negative charge, flow in and out of the capacitor continuously. At this point, there will be an instant current flow out of the capacitor and into the capacitor, but in the opposite direction of the negative charge. Here on the graph, it shows the current produced by the capacitor and is leading 90 degrees to the single-phase current of the motor winding. Like in the three-phase supply, motor is getting a two-phase supply now, with a 90 degrees phase angle difference. This will last only for a few seconds, but this period is more than enough to make the magnetic field to rotate, making single-phase induction motor to run on its own, without any starting issue. Further, you will see that the capacitor current is at its maximum when the rate of change of supply voltage is at its maximum. Although voltage value is 0 now, rate of change of voltage shown in black line is at its maximum here and is climbing upwards. So you get the maximum capacitor current at this point. When voltage value is at its maximum, you will see the rate of change of voltage is at 0 and is about to turn downwards now. Since rate of change of voltage is at 0, capacitor doesn't deliver any current at this point, and the value of current is at 0 here. When the rate of change of voltage is at its minimum too, voltage value shows 0. At this point, capacitor delivers its minimum current. In fact, it is the same value as its maximum, but flowing on the opposite direction. When motor is started, capacitor delivers its current first, starting from 0. After 90 degrees passed, and when capacitor current reaches its maximum value, single phase line current starts with 0 value. So it is clear, capacitor current is leading here by 90 degrees, with the required phase difference for rotating magnetic field. Within few seconds after start, centrifugal switch disconnects start capacitor, but induction motor will run, with its rotor conductors cutting the rotating magnetic field continuously. There will be instances where the torque requirement of the single-phase induction motor is not adequate, with start capacitor boosting it at the start only. On these occasions, we can introduce another capacitor to the auxiliary winding for continuous running like this, and it will be with much less value related to the start capacitor microfarad value. Now you will see, even after the start capacitor is disconnected, motor runs with run capacitor intact, with the auxiliary winding, providing the additional out-of-phase current, needs to run this motor with relatively higher torque. Run capacitors are capable of running continuously with the motor, but start capacitors cannot run continuously and need to be isolated with the centrifugal switch within few seconds. Hope you got fair idea now why capacitors are provided to run single-phase induction motors.